Well, good morning, and thank you for joining me on this rainy Monday. We're going to do chapter 3 today, but before we do that, I'd like to talk a little bit about the model that we made in experiment 1 and in enantiomers. In lab, you took your model set, you made two models that were the same. You were able to superimpose these and convince yourself that yes, they are exactly the same. Then what you did is you exchanged any two groups. Here I'm going to exchange the red and the purple. Then when you tried to superimpose, well, it no longer worked. Okay? Those don't line up. The whites do, the greens do, but these guys are reversed. What I suggested was that you take one of these and rotate it, something like that. So you wind up with something like this. And I said, imagine if there was a mirror right in between. This would reflect, those would reflect, and of course the purple is back in both. We said that these were enantiomers. They're mirror images. They are not superimposable on each other. Now this is a fancy little movie that says the same thing I just said. Here's our mirror. That's our mirror image. And when you move these to superimpose, obviously they don't line up. Enantiomers, a compound and its mirror image, are identical in virtually every physical and chemical property, except that they rotate the plane of plane polarized light. Hence they've earned the name optically active. Now what the heck does this mean? Well, light from a source has many planes associated with it. Polarizer basically has little slits that only allows a single plane to go through. You take your compound, the enantiomer, put it in solution, stick it in this beam, and by George, it rotates it. Now, you might wonder, who in the world ever thought to do this? Well, it was kind of an accident sort of thing, really. A gentleman, a Frenchman by the name of Jacques somebody, Francois somebody, was working on crystals, and crystals can also exist as mirror images. And he was using a polarized microscope, and notice this. This was in 1811. Here's a pair of crystals that are clearly mirror images of each other. This is ammonium tartrate. And this is one of the first things that Pasteur did, actually. Crystallized a mixture of the two enantiomers. They came out as mirror image crystals. Then took a fine pair of tweezers and literally separated them. Found one rotated one way, one rotated the other. Why this happens? Basically, baby physics tells us that plane polarized light can be described as two vectors, electric and magnetic. The resultant is the plane, so we do vector sum. And here we are. This is the plane of the light. If we pretend that the red vector here is absorbed by the purple guy, then when the light impinges upon this enantiomer, this will be absorbed. Now the vector sum looks like this, and it's rotated. But this guy, it's on this side, and the plane is reversed. Kind of neat. I said that this was a very central concept in organic and biochemistry. These are called amino acids. You may have seen these in some other course. They all feature a central carbon that has a hydrogen, an amino group, and a carboxylic acid. Hydrogen in this case is pointing back, this goes forward. They all have this same central feature, and then they have a side chain that's different. There are 20 side chains like this. They all have different water solubility. This is charged, so it's very soluble. The water solubility of these guys, so these are very insoluble over here. These are very soluble. The water solubility is what dictates the shape of the protein that it folds into. So, kind of neat. Any questions? All right, well, Chapter 3, Chemical Bonding and Nomenclature. This is ammonia. It turns out that ammonia also has tetrahedral geometry, just like the model we built. The fourth position here is actually occupied by a pair of electrons. If you put something here, you can actually have a chiral nitrogen compound, if you have four different things. All right, we had defined matter, we defined elements, and we talked a little about compounds. They can be broken down into simpler substances. The model we looked at was methane. This is a carbon in the middle, 4 hydrogens. This is what is referred to as a molecular compound. It's a molecular compound that, hence this is a molecule. It's a molecular compound because the electrons are shared here between the carbon and the hydrogen. These bonds represent shared pairs of electrons. The other type of compound is ionic. We'll talk about that in a second. The covalent bonds that we make here, that's the word for the shared electrons, can be single. You can actually make double bonds where we share 4 electrons, or triple bonds where we share 6. Ionic compounds. For an ionic compound, we're going to transfer an electron from metal to a nonmetal. This gives a positive sodium and a negative chlorine. In a solid state, these all clump together in an array that has a particular geometry that's based on basically how well they pack together. Now, we had talked about carbon. When we did carbon, I said we have 2 energy levels. The configuration is 1s2, 2s2, 2p2. The core electrons are here in the middle. That's the 1s2. And the higher energy electrons are called the valence electrons. Now, a long time ago, this is like 1870s, people knew that compounds existed, but they really had very poor understanding of bonding. A gentleman by the name of Lewis came up with a very simple way to predict bonding using what's called Lewis dot structures. Basically what he said, using carbon as an example, is the first thing you do is write the symbol for carbon in the middle. Now, we just said 2s and 2p electrons, highest energy, they're valence electrons. There are 4 of them. So we said what you do is you put 4 little dots around your carbon. They go in one at a time, singly, like that. This is the Lewis dot structure for a carbon atom. Now, if you have more than 4 valence electrons, you start to pair them up one at a time. Let's look at fluorine for that. There it is. Fluorine is also second period. It has 1, 2, 3, 4, 5, 6, 7 valence electrons. We would put 4 around one at a time. Then we would add the rest, making pairs as we go. Now, a Lewis structure is just a bookkeeping tool. It doesn't matter quite how you draw it up and down, sideways, but where this missing electron is doesn't matter. All of these are equivalent structures, just bookkeeping. Any questions? All right, what's a simple way to know how many valence electrons you have? Remember, we looked at our periodic table and said we would have 8 groups going across, even though there are 18. But we'll only pick out the representatives, groups 1 through 8. If you simply look at the group number, it tells you the number of valence electrons. Everything in group 1 has 1 valence electron. Group 3, 3 valence electrons. Group 8, 8 valence electrons. By the time you get to 8, it's full, isn't it? That's a very stable state. We're going to make bonds by sharing electrons. Here we're already full. Can't share. Actually, you can, but that's another course. All right, let's talk about ionic compounds first. We said that in sodium chloride, we transferred an electron from the sodium to the chlorine. That leaves the sodium positively charged. The word for that is a cation. The electron is accepted by the chlorine, makes it negative, and is called an anion. When you do the Lewis structure for an ion, you just start off with all of the electrons, then you add or subtract as necessary. Chloride anion. There's chlorine, so we'll write our Cl. We have 1, 2, 3, 4, 5, 6, 7 valence electrons. We put 7 little dots all around it. One at a time, then you pair them up. All right, to make the chloride anion, it has a -1 charge, so we need 1 extra electron. We do that by simply taking the donated electron and pairing it up. That is the chloride anion. Isn't that simple? Let's do sulfide dianion. First step, sulfur is somewhere. Here it is. It's in group 6. We start off with our sulfur as an S, and we're going to put 6 electrons on. So we have 2 unpaired electrons. Electrons, we remember, like to be paired up. Opposite spins, paired up. To make the dianion, all we simply do is add 2 electrons. and show the charge. Very quickly draw the nitride anion for me. Nitrogen is here in group 5. You, of course, start off with the big N. We are going to have 1, 2, 3, 4, 5 valence electrons. Now, to make the trianion, we need to add 3 more. And there it is. Let's do one more. The sodium cation. Sodium is here in group 1. Here it is. It's sitting right there in group 1. Symbol is Na, so we'll put our Na. Because it's group 1, it will have 1 valence electron. And in sodium chloride, what did we say happens? It's going to donate this electron to the chlorine, leaving it 1 short and a positive charge. Any questions? Well, I hope you've noticed that there's a pattern here. I said by the time we get to group 8, the valence level is full, okay? That's 8 electrons. That's called the octet rule. Inert gases here are inert because the valence shell is full. As we've been doing our exercise here, we took chlorine, which is here in group 7, added 1 electron, and we basically moved it to the configuration of argon, an inert gas. We have filled the shell. This is the octet rule. Atoms love a full shell. For sulfur, we started off here. We added 2 electrons. And again, configuration of argon. For sodium, we started off here. We're going to lose this electron. When we do, we get the electron configuration of neon. The octet rule. We'll see that there are exceptions, and we'll see some of them. But basically, atoms want to hit the inert gas. Any questions? Yeah.
So if lithium was to lose an electron, it would turn into blue.
Yeah. Same configuration as helium. All right. So much for ionics. Let's do covalent. Chlorine exists as 2 chlorine atoms bonded together, CO2. Chlorine is group 7, it has 7 valence electrons. To make a covalent bond, all you do is bring in the other chlorine and you share these electrons. Does this fit the octet rule? Of course it does. You count the shared pair for both. So this guy has 2, 4, 6, 8. This one also has 2, 4, 6, 8. Any questions? When we write a covalent bond in a compound, we typically don't put little dots. We get tired of doing dots. We use a dash. And whenever you see 2 atoms joined together with a dash, you interpret that as this is a covalent bond and it has 2 electrons in Any questions? Well, let's make a compound. We saw ammonia earlier. Let's do the Lewis structure for ammonia. We need to find nitrogen and hydrogen. Nitrogen is here in group 5. Hydrogen is here in group 1. Let's start off with our nitrogen. Now we have 3 hydrogens to put around it. Remember, we want to form bonds, covalent bonds. Hydrogen will have 1 electron, so we simply space them around like that. Scooch them all together. Our nitrogen now has 8, so it's really happy. Hydrogen, because it's group 1, the inert gas it goes to is helium, 2 electrons. So not quite an octet, but so full. Every hydrogen has 2, the nitrogen has 8. We would draw it something like this. And again, this is referred to simply as a single bond, 2 electrons, and this is an unshared pair of electrons, like we saw on the first opening slide. Any questions? Well, let's do it again. For nitrogen, we all are familiar with nitrogen. We breathe it in and out all day, hopefully. 2 nitrogens stuck together. All right, nitrogen we said is group 5. So each nitrogen starts with 5 electrons. What we have to do is somehow rearrange our Lewis structure here so that each nitrogen has 8 valence electrons. So remember, this is just bookkeeping. We can move these electrons if we want. Let's start off by taking these guys, moving them in between the nitrogens. When we do that, this nitrogen now has 2, 4, 6, 7 electrons. So there's the other one. That's better than 6. But if we move these guys up, we now have 3, 6, 8, 3, 6, 8 around each nitrogen. This is nitrogen number 1 and nitrogen number 2. This represents a triple covalent bond. Each of these shows up as a separate dash. The bonding between the 2 nitrogens is extremely strong because of the triple bond. Any questions? Well, I will pause for a minute. And why don't you see if you can do carbon monoxide? Carbon is here in group 4, oxygen in group 6. So this is what we're starting with. Right now, this oxygen has 2, 4, 6, 7. The carbon has 2, 3, 4, 5. Not very fair, is it? So let's do like we did with nitrogen and share a couple and move them in to make a double bond. When we do this, this oxygen now has 2, 4, 6, 8 electrons. It's happy. But poor carbon has 2, 4, 6. Well, shoot. Oxygen is very cooperative, however, and it will take one of its extra pairs, move it up. Let's also get this guy out of here and pair it up, because electrons like to be paired. Now we have a structure with 8 electrons around the carbon, 8 around the oxygen. Once again, we have made a triple bond. Carbon, oxygen. Carbon monoxide, as we all know, is toxic. The reason it is this pair of electrons on the carbon, the unshared pair. Carbon really likes 4 bonds. There are 3, and this one is just hanging there. This pair will bind to the iron in hemoglobin very tightly, gives carbon its 4 bonds, also means that hemoglobin cannot carry oxygen. Hence you die. All right, Lewis structures. This guy is different than all of the other tutorials. It's not algorithmic, it's based on graphics. The reason it's useful is that it has rules. Now, when I draw a Lewis structure, I just kind of look at all the little dots and say, well, gee, I could do this, 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 and this. Okay, that's what I do. By inspection. If you don't like inspection, here are rules. So let's look at it by the rules for CO2. Rule 1, count the total number of electrons and hydrogens. Well, no hydrogens. Total number of electrons. There's a valence electrons. Carbon has 4. Each oxygen will have 6. Group 4, group 6. 16 electrons, and of course, no hydrogens. That's step 1. Step 2, draw your central atom and attach all the hydrogens, the other atoms, not hydrogen, and give everybody that you've attached an octet. So, here's our oxygens. We have given each of the oxygens an octet. That's our central atom. Carbon only has 4 electrons at this point. It says place any remaining electrons on the central atom. That would be our carbon, but we've used 8, 8, 16. That's all the electrons we have. No more remaining. All right. Finally, make double or triple bonds to give the central atom, that's our carbon, an octet. So we can do that very simply by moving electron pairs in, like that, and that. And there is our Lewis structure for CO2. So, if you like to just take and draw these things in your head, do it. If you want to follow rules, here are the rules. All right. Nobody's perfect, not even Lewis. An example, Lewis said everything needs 8, right? This is SF4. It's a real compound. And let's look at it. It has 2, 4, 6, 8, 10 electrons surrounding it. This is called valence expansion, and let's see where this comes from. So let's go ahead and draw SF4. Sulfur, again, is right here. Fluorine is group 7. Draw our sulfur in the middle, and we're going to put 4 fluorines around it. Well, okay. I look at this and I say, that's good. I can make a bond here, right? That's good. But every bond can only have 2 electrons. And we have 3 and 3. Well, shoot, what do? What I'm going to do is simply take 2 of these electrons. Remember, it's bookkeeping. So I'm going to put these in some place that I call storage. There they go. Now they're gone. I remember that I have 2 sitting in the corner here, right? Now it's no problem making 1, 2, 3, 4 bonds, except that we have our 2 electrons in the corner. What do we do with them? They go back on the central atom. Now we have 2, 4, 6, 8, 10 electrons around our sulfur. Again, this is valence expansion. Valence expansion happens in elements above the second period, so that's third period. Anything in the third period down can have up to 16 or so electrons around it. Everything else, we keep it simple, and we just use the octet rule. The extra pair, where does it go? It's called a hybridized orbital. You take the space for 1s, 3p's, and 1d orbital, combine them, calculate a region of space, and you come up with this geometry. Trigonopyramidal is called. Any questions? All right. Blackboard has a tutorial dealing with this stuff. Sometimes, well, let's just look at a question. Draw the Lewis structure, or in the Lewis structure for ClF3, there are blank electrons around the chlorine, and how many double bonds? So this is a valence expansion problem. Chlorine trifluoride. Fluorine is here, fluorine's right above it. They're both group 7. There's our chlorine, there's our 3 fluorines, and let's put in all the electrons. There are 28 total valence electrons, right? We have 7 times 3, 4. 28 total valence electrons. First thing in the rules, we put an octet around each of the fluorines. So we're like that. Now, how many electrons have we used? 8, 16, 24, right? That's right. That means we have 2 excess electrons. Those go on the chlorine, like that. ClF3 looks like this. So, how many electrons around the chlorine? 2, 4, 6, 8, 10. How many double bonds do we have to make? None. On Blackboard, you would simply enter 10 electrons around the chlorine. Is it 2, 4, 6, 8? Yeah, 10. And 0 double bonds. Any questions? All right. How do you know if you have a molecular compound or an ionic compound? It's actually extremely simple. What you do is you look at the formula for your compound and you look to see if it contains a metal. Remember, in our periodic table here, we said everything blue was a metal. These guys were nonmetals, and these guys were semimetals. If your compound contains only nonmetals and or semimetals, it's molecular. Remember, hydrogen is over here. It's technically either one, but we'll call it a nonmetal now. If your compound contains a metal, any metal at all, it will be ionic. Very simple. Look and see where your compound is. If it's a metal, it's ionic. If it's not, it's molecular. Magnesium chloride. Well, we look at our periodic table. Magnesium's a metal. Chlorine's a nonmetal. This is an ionic compound. Hydrogen fluoride. Hydrogen is a nonmetal. Fluorine is also a nonmetal. This is molecular. Covalent bond between the hydrogen and the fluorine. Silicon tetrafluoride. Silicon, it's a semimetal. Fluorine is a nonmetal. This is a molecular compound. Sodium bromide, once again, metal, nonmetal, it is ionic. How about this? I said that chlorine existed as a diatomic molecule. Two chlorines stuck together, right? Well, sulfur exists as 8 sulfur atoms stuck together. Is this molecular or is it ionic? Sulfur is a nonmetal, therefore this is a molecular compound. Looks like a little crown, kind of cute. Each of these are covalent bonds. All right, let's just look at a sample here and decide if they're going to be molecular or ionic. Nickel chloride. Nickel sounds metallic, doesn't it? Nickel is right there, making it ionic. Dihydrogen sulfide. Hydrogen is nonmetal. Sulfur is nonmetal. This is molecular. Silicon tetrahydride. Silicon, where is it? There it is. Tetrahydride, they're both nonmetals, molecular. SO3, nonmetal, nonmetal, molecular. Calcium hydride, calcium is here in group 2, it's a metal. Hydrogen is a nonmetal, but it's still ionic. Why don't you just quickly jot those down? Our first one here is cesium oxide. Cesium, group 1 metal. Rule is if it's got a metal, it's ionic. Diiodine heptaoxide. Iodine, oxygen. They're both non-metals. This is a vapor. Oxygen difluoride. Non-metal, non-metal, molecular. Carbon tetrahydride, also called methane or natural gas. We have non-metal, non-metal, it's molecular. And finally, quite obviously, sodium chloride we've talked about. Sodium is a metal. This is ionic. Any questions? All right, let's talk a little more about ionic compounds. Remember, we have a positively charged ion called the cation. Negatively charged is the anion. And they kind of stick together because they have opposite charges. In the solid state, these pack together to make crystals. And again, it's the size of the atoms and their charges that dictates the packing. For sodium chloride, the packing is cubic. And if you look at nice crystals of sodium chloride, these are very sharp edges. And that's due because this is an extensive cubic array. The bonding here is simply electrostatic. All right. How do you know what charge you have for the various ions? Once again, we're going to use our group numbers. Starting here with group 1. Things in group 1 will tend to lose an electron and become +1. Group 2 +2. Group 3 +3. Group 4 +4. Simple as it can be. By the time you get to group 5, however, it is energetically easier for the atom to accept electrons instead of donate them. So group 5 is a -3, -2, -1, and of course, inert. Everything 4 and below will form ions, cations. Everything 5 and above will give an anion. Remember, what we're doing is simply adding 3 electrons to get here to neon. 3 electrons to argon. 3 electrons to krypton, whatever. Any questions? All right, if we go to assemble an ionic compound, what we have to do is first recognize the charges. The compound itself must be neutral. So you need as many positives as you have negatives. For magnesium sulfide, we have a +2 and a -2. That's group 2, that's group 6. Net charge is 0. Sodium bromide, +1, -1, again 0. Here we have sulfur that has 2 negatives, so we need 2 sodiums to balance it. 2 times 1, -2, again 0. Magnesium bromide, same thing, we're getting to 0. When we go to write these compounds, even though we know, say, sodium chloride exists as a huge array in the solid state, what we do is we write the simplest whole number ratio. So for magnesium sulfide, we would just do MgS. Mg2S2 would also be neutral. That's not the lowest whole number ratio. You do the simplest ratio. Sodium bromide, NaBr. Sodium sulfide, Na2S, Na sodium times 2 plus a sulfur. And finally, magnesium bromide, 2 are magnesium and 2 bromines. Any questions? Going backwards, interpreting a structure. Sodium chloride, 1 sodium, 1 chlorine. 1 hydrogen, 1 fluorine. Remember, the 2 tells us how many we have, 2 hydrogens and an oxygen. And this is potassium sulfate. 2 potassiums, 1 sulfur, 4 oxygens. We'll see that sulfate, SO4, exists as a unit, but that's coming up. Any questions? Well, let's write a couple formulas here. Magnesium and chlorine. What you want to do first is find everybody. Magnesium is here in group 2. Chlorine is in group 7. Magnesium will be a +2. Chlorine will be a -1. Remember, the compound must be neutral. So we have to get 2 chlorines for every magnesium. To write the formula, you simply write 1 magnesium and 2 chlorines. Any questions? Let's do something a little more interesting, aluminum and oxygen. Aluminum is here in group 3. It'll form a +3 ion. Oxygen is in group 6. It'll be a -2 ion. Aluminum +3, oxygen -2. What we have to do is fiddle with the ratio to get a neutral compound. But there's a shortcut that actually comes in handy every now and then. The shortcut to get the ratio. What I do is I simply write the ions, +3 -2. Then I do ALO. The 3 is the subscript for the oxygen. The 2 is a subscript for the and there it is, aluminum oxide. Simple symmetry crisscross. When you do this, you have to be careful. Beryllium and selenium. Beryllium is there in group 2. Selenium is here in -3. So if we did our crisscross here, we could do this, and we would write this. But then immediately we would say to ourselves, wait a minute, that's not the lowest whole number ratio, is it? Get rid of that. It's just BESE. That's what it looks like. Little tiny berylliums, big seleniums. Again, cubic structure. Any questions? Well, I'm sure everybody secretly has a question, okay? I call this beryllium selenide. How did I know that? Because I know nomenclature. So let me share this with you. Nomenclature of binary ionic compounds. What we're going to do, we're going to have a cation and an anion. The cation, first word in the name, is simply the element. The anion, we take the root of the element, like sulfur is sulf, and we add ID. If you happen to have 12 of these, doesn't matter. You do not use multipliers in ionic compounds. So, it's a magnesium. Our first word is magnesium. Our second word, we have bromine here. The root is brome. And we're going to add IDE. Magnesium bromide. Well, that's simple. Sodium. Root for chlorine is chlor. I. Sodium chloride. The root for sulfur is sulf. This is potassium. Potassium sulfide. Beryllium bromide. That's so simple I could do it, right? Don't have to worry about multipliers. Well, let's just prove that you can do it too. Quickly jot down names for these guys. Our first word here, the element Ca is calcium. Bromine is bromide. Aluminum, oxygen, the root is ox. Aluminum oxide. Lithium, sulfide. Calcium oxide. Nickel chloride. However, this is wrong. We will explain why it's wrong soon. This is actually nickel 2 chloride. Roman numeral 2, it tells you the charge on a nickel. We'll see when we have to do this in just a bit. So this exercise is really simple, okay? Really simple. Take these names and write a formula. All of a sudden you're saying to yourselves, gee, I wish we had multipliers, aren't you? Because it would make it so much easier. You have to look and say, okay, calcium, that's group 2, gonna be a +2, right? Nitrogen, group 5, it's gonna be a -3. What you need is a ratio for these two. Here's where you can use your crisscross. You're gonna have 3 calciums and 2 nitrites. That worked. Magnesium oxide. Magnesium, group 2. Oxygen, group 6. This is +2, -2. All we need is 1 to 1, MgO. Lithium iodide. Lithium, group 1. Iodine, group 7. This is +1, this is -1. Need a simple 1 to 1 ratio. Barium phosphide. Barium is here at group 2. It's a +2. Phosphorus over here in group 5. It's a -3. Once again, crisscross. 3 bariums, 2 phosphorus. Beryllium fluoride. Beryllium is there in group 2, so it's a +2. Fluorine is group 7, it's a -1. Need 2 to 1. Any questions? All right, well, let's delve into the question of why nickel chloride was wrong. Oh no, before we do that, we get to do polyatomic ions. So let me just back up and do my intro. This is fairly simple, right? If ionic compounds stopped here, naming them would be okay. We could do that. Unfortunately, there's a ringer. The ringer is called a polyatomic ion. Strontium sulfate. Strontium. Group 2 +2. Sulfate. Sulfate is a collection of 1 sulfur, 4 oxygens, and this group, this covalent group, this molecular group, has a charge of -2. Here's our sulfur in the middle. How many electrons around it? 2, 4, 6, 8, 10, 12. And here are 2 negative oxygens. These simply stick together. Think of it as a little ball and a big ball stuck together. This is a unit. Unfortunately, polyatomic ions, there are a lot of them. This is a very slightly partial list of them. And even more unfortunately, you have to kind of know them, at least the important ones. Acetate, CH3COO minus, carbonate CO3 minus 2. Hydrogen carbonate with stick a hydrogen on, cyanide CN, nitrate NO3, nitrite NO2, ammonium. This is the only positive one that we're going to deal with. Hydronium hydroxide, chromate dichromate, perchlorate, chlorate, chlorite, sulfate, hydrogen sulfate, sulfite, hydrogen sulfide, etc., etc. These are your basic important ones. Down here, these guys you would use in general chemistry lab. We will use these when we get to chapter 8, acids and bases. Everything else we pretty much use all the time. So, there is a system to this nomenclature. oxygen-containing polyatomics. So we have a central atom, like sulfate, central sulfur, 4 oxygens around it, okay? Step 1, you identify the parent for sulfate. Sulf is the root, you add ATE. For chlorate, chlor is the root, you add ATE, chlorate. Now, if we add one more oxygen around our central chlorine here, we would have perchlorate. Per goes in front. If we take one oxygen off the parent, we get a suffix of IT, ite. If we take 2 off, we get hypochlorite. The only really redeeming thing is all of these have the same charge. So let's see how this works. Chlorine containing, this is chlor, ClO3, chlor is our root. This is our parent, so it's chlorate. If we add an oxygen, we make ClO4, perchlorate. If we take one oxygen away, we get chlorite. If we take 2 oxygens away from our parent, hypochlorite. Again, all of these are -1. Sulfur ions. Sulfate, we've seen, SO4. Sulfate is our parent. There is a persulfate where we have SO5, but if we take one oxygen away, we get the much more common sulfite. We can take one of these negative oxygens and stick a hydrogen on it. When we do that, we neutralize one of the charges. We would name this hydrogen sulfate. Likewise, sulfite, hydrogen sulfite. 2 words. Phosphorus, our parent, phosphate. 1 oxygen gone, phosphite. Here we have 3 negatives. So we can put 1 hydrogen on and do hydrogen phosphate, or we can put 2 hydrogens on and do dihydrogen phosphate. Same thing with phosphite. Carbon. The parent is carbonate. There is no carbonite. Carbonite was from Star Wars. Again, we have 2 negative oxygens. We can put a hydrogen on and make hydrogen carbonate. Acetate, cyanide, you will use these extensively in general chemistry. Cyanide, triple bond between the carbon and the nitrogen. Just like carbon monoxide, this binds to the iron and hemoglobin. That's why it's toxic. Nitrogen. Nitrate is our parent. 1 oxygen nitrite. And finally, ammonium. This is the only cation that we're going to deal with in this class. NH4 plus 1. Any questions? Again, this is general chemistry lab, chromate and dichromate. I show them because on Blackboard, they will show up occasionally. Chromate, CrO4, dichromate, Cr2O7, again, they're both -2. Very nice, solid. What you do with this stuff in lab is dissolve it in water concentrated solution. It's a fabulous oxidizing agent. Use it to clean glassware. All right, let's see how we put together a polyatomic. Let's do fluorine. Once again, fluorine here in group 7, oxygen in group 6. There's our 7 electrons. Each oxygen has 6. All right, so let's look here. We're missing an electron here. There. Here we have 3 electrons in a bond. That's not going to work. That's not going to work either. Let's start by getting rid of these guys. Let's do this. And let's move this guy down here and carry it down. This gives us this. Now, oxygen has 8 electrons, both of them. This oxygen only has 6, 7. The chlorine only has 7. But remember, this is an anion. So somebody somewhere is going to donate an electron to it. It's going to go on the chlorine. When it does, this whole group becomes negative. Scooch them all together. We have 8 electrons around each oxygen, 8 electrons on the chlorine. This is how you would write it. If you were doing a Lewis structure, you need to show that the entire complex, these are covalent bonds, has a negative charge. This is kind of what it looks like in real life. That's our chlorine. We have 3 oxygens and a pair of electrons. Looks a lot like ammonia. Any questions? All right, naming these guys is simple if you remember what they are. Carbon with 3 oxygens. Carbonate, it's the parent. There is no carbonate. Calcium carbonate. NH4 plus was ammonium. Cl minus chloride. Sodium sulfate. Lithium sulfite. Potassium hydrogen phosphate. 3 words. Now going backwards, again we have the problem with no multipliers. Potassium sulfate. Potassium is going to be +1. Sulfate is -2. 2 potassiums for every sulfate. Sulfite here is going to be -2. Barium is +2. Simply 1 to 1, 1 less oxygen than sulfate. Aluminum is +3. Chlorate is going to be -1. 3 chlorates for every aluminum. Now, how do we show this? We use parentheses. This is important. ClO3, 3. We have 3 chlorates and 1 aluminum. Silver nitrate. Silver is +1. Nitrate is -1. Simply AgNO3. Barium cyanide. Barium is +2. Cyanide we said was -1, we need 2 cyanides. Again, we use parenthesis like this. If we simply stuck the 2 without the parenthesis, it would look like 1 carbon, 2 nitrogens, wouldn't it? That's not right. Any questions? All right. Everybody is in a slight panic now because you're sitting back saying to yourself, gee, I've got to memorize all that stuff, really? My head's already full. Well, when we take our first and second hour exams, you are allowed 1 3x5 card, and one side you can write anything you want. Now this does 2 things. If you just can't figure out how to remember polyatomics, write them in a very, very, very small handwriting in the corner. In addition to helping your memories, this also teaches you to write very small. 3x5 card, 3 inches by 5 inches, not 3 feet by 5 feet. Okay? It's what I call the memory aid. Any questions? All right, let's name a few more. Pb is lead. This is oxygen, right? It's ionic. It is lead oxide. Pb is still lead. This is still oxygen. This is lead oxide. This is iron oxide. This is iron oxide. This is iron oxide. Wait a minute. We have a bit of a problem here, don't we? The problem is lead and iron are transition metals. These guys in the middle, they can assume different charges. The charge they assume is referred to as its oxidation number. Fancy word, but it's still just the charge. Oxidation number compares the element in the periodic table with the element in your compound. For iron, in the periodic table, it's 0 by definition. In a compound, it can be +2 or +3. If we had magnesium bromide, we simply look at this. The charge here is +2, -1. In terms of oxidation numbers, +2, -1. Same thing. Lithium phosphide, lithium +1, phosphorus -3. Oxidation numbers +1 and -3. The same as the charge. All right, my goodness, another set of rules. We're going to see these rules and use them in Chapter 5. Something to look forward to. For right now, however, out of this whole list, you need to know this. With a few exceptions, oxygen will be -2. Halogens will be -1. That's their oxidation numbers. -2 and -1. So, PbO, our oxygen is going to be -2, isn't it? To make this neutral, the lead must be +2. The oxidation number is therefore +2, same as the charge. Oxygen is still gonna be -2 here. We have 2 of them, that's 4 negatives. This lead, therefore, must be +4. Iron sulfate. Sulfate is a polyatomic, it's fixed at -2. That means the iron here must be +2. Oxygen is still going to be -2. We have 6 negatives. In order to make it neutral, we need 6 positives. That means each iron must be +3. A little bit of a bother, but not too much that you can't do. How do we show this? Well, remember nickel chloride. We're going to use Roman numerals in parenthesis after the element. So, we said this lead must be a +4. Therefore, this is going to be lead, Roman numeral 4 in parenthesis, oxide. 2 words, no space here. This lead must be -2. Lead, 2, oxide. Carbonate, polyatomic, -2. Iron must be +2. Iron, 2, carbonate. Halogen is going to be -1. We have 3 of them. Iron must be +3. Iron, 3, bromide. Entirely doable. Now, to help you with nomenclature, we have tutorials. This is binary ionic. It will give you a formula and you enter the name. Spaces count, so make sure you don't enter stupid spaces. This is barium, isn't it? This is iodine. We're going to have barium. Barium is not a transition metal. We don't need to worry. It's here in group 2. We don't need to worry about the oxidation number. We simply write barium iodide. CuI. First thing to note, copper is a transition metal. Right there in the middle. You need to show the charge. Iodide will be -1. This is going to be copper 1 iodide. ClO, what is that? We have taken 2 oxygens off the parent, so it's a hypochlorite. Bleach is sodium hypochlorite. Hypochlorite. It's -1, they all are. There are 3 of them. Iron must be +3. It's a transition metal. We have to do iron 3 hypochlorite. Any questions? All right, well, aside from the shock of polyatomics, naming ionic compounds is doable. But naming molecular compounds is even easier. Why? Because we use multipliers. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. That's how you count to 10. What we're going to do is just like with an ionic compound, element comes first, add IDE, and then you use multipliers. If you only have one and it's the first element, you don't use mono. If you have two or three, you use the multiplier. For the second part of the name, you always use a multiplier. That's it. CCl4. They're both nonmetal, so this is molecular. Our first word is just the first element, carbon. Don't use mono. We have chlorine here, that's chloride, and we have four of them. How do you say four? Tetra. Carbon, tetra, chloride. Two words. This is sulfur, this is oxygen. We have two oxygens. Our first word is simply going to be sulfur. Our second word, we have to show there are two, that's di. Two oxygens, dioxide. NO2. Here our first element has two of them. Here we have to use a multiplier. So this is going to be dinitrogen as our first word. We have one oxygen, but we have to use mono for the second element. So this is going to be monoxide. Now, you may notice that I'm missing an O here. Two O's in a row doesn't work very well. If you have two vowels after you add your multiplier, typically you change it and just dump one of them. We'll see that now. Again, this is two nitrogens, so it's a dinitrogen. 5 is penta. So this is pentaoxide. But instead we write pent, the AE is gone. AO. Any questions? Well, then do some. Carbon, two oxygens, that's going to be carbon dioxide. Two hydrogens, one sulfur. Use our multiplier. Dihydrogen monosulfide. One silicon, four hydrogens. Silicon tetrahydride. One sulfur, three oxygens. Sulfur trioxide. One nitrogen, three chlorines. Nitrogen trichloride. Now do these and I'll hush. Four phosphorus, not potassium. That's tetraphosphorus. 6 is hex, hexasulfide. Two iodines, diiodine. 7 is hept, heptoxide. Drop the A. 1 oxygen, 2 fluorines. Oxygen, difluoride. Carbon, tetrahydride. If you called it this, nobody would know what it is. This again is methane. Tetrasulfur dinitride. Now going backwards is even easier. 1 nitrogen, 3 iodines. 2 phosphorus, 5 oxygens. 1 sulfur, 3 chlorines. 1 nitrogen, 1 oxygen. No. 1 hydrogen, 1 chlorine. Later on in chapter 8, we will call this hydrofluoric acid. Any questions? All right, let's look at the next tutorial here. This is binary molecular compounds, formula to name. We have 2 nitrogens, that's a dinitrogen. We have 3 oxygens, that's a trioxide. Multipliers are di and tri. 2 words, dinitrogen trioxide. NS. 1 nitrogen, we don't use mono. 1 sulfur, we do use mono. Nitrogen, monosulfide. All right, names to formulas. You obviously can't do supers and subscripts either here or on Blackboard. So the tutorials work the same way. Aluminum sulfate, you simply put everything in line. Okay? Sulfur tetrabromide. 1 sulfur, 4 bromines. Sodium phosphate. 1 sodium, 1, no, I'm sorry. Sodium is +1. Phosphate is -3. So we need 3 sodiums and 1 phosphate. 3 sodiums for every phosphate, Na3PO4. All right. I think we're just about done with the chapter. On Wednesday, we are doing lab number 3, which is density. In the density lab, we're going to do a bunch of measurements and stuff like that again. But one of the things that you're going to calculate, amazingly, is the thickness of aluminum foil. We will weigh a chunk of aluminum foil, measure its length and width, and calculate the thickness. Kind of magic. Today we added Lewis structures, ionic compounds, molecular compounds, and named to formulas. Remember, these are worth 5 points each as extra credit, added to your point total. It's the same as adding it to your first hour exam. There's a lot here already. Please make sure you do these. They must be complete before we do our first hour exam. Got it? All right, guys, have a good day.
Dr. Smith.
Hello.
I didn't come to lab last Wednesday.
Right.
Yeah, last Wednesday because I sent an email, but I don't know.
No, I did. I responded to it actually.
Oh, you did? Okay.
Yeah.
I have to check.
Sadly, we can't make up labs. Yeah. Can't make up labs, no. Because they would have to prep the whole lab for one person. That doesn't work. So just make sure you do lots of tutorials to make up for it.